Hello, everyone. Can you hear me? Okay, cool. Good afternoon. My name is Amelia Kawasaki. I am a data science researcher at a security for AI startup out of Austin called Hiddenlayer. And when I'm not doing that, I'm also a PhD student at Oregon State University. And I'm here on behalf of myself and my co-authors, Andrew Davis and Houssam Abbas, to talk to you a little bit about the research that we've been doing with securing large language models using residual stream activation analysis. Cool. Thank you. I was going to open this slide set giving a little bit of a background on large language models, also known as LLMs, but I don't really think we need that at this point. I think this has been talked about quite a bit. The only notes I do want to make here are the difference between white box and black box LLMs. I don't know that we've defined yet. We all know the popular black box LLMs like ChatGPT and Claude. Those are the types of LLMs where you can only interact with these models through maybe a web interface or a coding API. Whereas the white box models of these are completely open to the public. You can download them off the internet. You're able to interact with the model at any point in the process as you're providing an input and an output. Okay. There's also, I don't want to qualify to you again why we need to defend these. I think at this point we mostly know. If you'd like to talk to me about that later, feel free. But let's start with current LLM attack detection frameworks. These are just a couple of state-of-the-art detection frameworks that I've seen out in papers in the wild. And let's note here that these are detection frameworks. So when the attack prompt goes into the model, we want to be able to detect that, not just defend against it, not just harden the model. So these are a couple of the ways that we know that this can be done. First, maybe the most basic, is just a basic regex detection on an input prompt into the model. So this works really well. However, some of the limitations here are that it only works for known attacks, right? You have to be able to write the regex string to do the pattern matching. And regex strings are very fragile. So those are the downsides there. Secondly, there's a different type of detection mechanism called a perplexity-based detection. And perplexity is a measurement that compares the training distribution that a model has seen of all the tokens that it's trained on to with the prompt that you're putting into it. And if the prompt is severely out of distribution, then this perplexity measurement will be high, and you'll be able to detect what is known as this token level attack. So when we say token level, what we're saying is these attacks are not what we've seen in the training data set. And I'll have some examples of what that'll look like. But a very well-known example of this type of detection that came out in 2023 reduces the attack success rate to 0% for all of their reported cases, which is really great. And this is a very legitimate way to detect the attacks. However, as I've mentioned, one of the big limitations here is that it can only work on token level attacks. And then finally, the third method of detection for attacks is just use more LLMs, stack another LLM on it. If you have a model that you're trying to protect, let's grab a second LLM that will look at the input and the output that that original LLM is getting and try to decide if this LLM has violated any content filters that you set up. This, again, very legitimate way to detect attacks. This popular example that came out in 2023 was able to reduce attack success rate by 77% on average across all of its reported attack types. Of course, the limitations here are mostly compute and optimization based. You're essentially doing 2 inferences per input into a model, which can cause a problem in some deployment cases, basically. Okay, so with all of this, is it possible, oh dear, I think these are the old version of the slides, but we'll just work with it. Is it possible to leverage our understanding for how large language models themselves process internal information to create a defense that would both cover all types of attacks and can generalize to new attacks and ideally does not require the use of additional LLMs? Is this possible? Well, we'll see. Kind of yes and kind of no. Let's talk about this detection framework that I've been proposing. So if we start with the LLM, the model, and we have a prompt and we have an output, what I'm suggesting, and what is also echoed in related works up until this point, is that you can extract data out of the model known as residual stream activations. And this is data that, well, we'll talk about it in a second. But basically, once you have that data, you can stick a binary classifier on it of your choice. I'm choosing light GBM for this point. And we can train this classifier on a set of activations that correspond to attack prompts and a set that corresponds to benign prompts. And from then on, whenever you're inputting any prompts into the model, you'll be able to get a score from the classifier about whether or not it thinks it is an attack on the model or not. Okay. Just to go a little bit more in detail, but not too much in detail because I do have a lot of results that I want to get through. What's important to note here is that I've trained a classifier on activations that come out of every layer for this model. So if we think about transformer-based large language models, there's multiple transformers, multiple layers. So for example, one of the models that I'm using here, Llama 2 7B, has 32 transformer layers. And each of these layers will modify the residual stream after the data goes through the layer. And so as a result, you'll have 32 sets of data that you can use to train classifiers. And in this case, for this experiment purpose, I'm training 32 separate binary classifiers to see if there's any difference in how the information is processed as it goes through the model, basically. Cool. All right. Now the more interesting part. How did I test all of this? I used a variety of white box models. Remember, we can only do this with white box because we need to extract information out of the middle, including Llama 2, wasn't able to get to Llama 3 yet, smaller versions of Llama, other versions, anything I could really get my hands on at this point, including an uncensored model that supposedly does not have content filters on it to see if that would change the results at all. And I used a bunch of different data sets that have both benign prompts and attack prompts. And the reason for this, what I did here is I took one benign set and compared it with one attack set. And the reason for this, and as we've sort of touched on in this conference so far, what we define as an attack is very context dependent. It depends on how the LLM is deployed. Say an attack on ChatGPT will not be the same as what we consider to be an attack on a customer service-based LLM. And so as a result, I wanted to test this framework with multiple different types of attacks, styles, topics, just to make sure that this detection framework will work regardless of what scenario we're deploying this in, basically. Note, and importantly, not all of these data sets are guaranteed to be successful attacks on the model. And this is very important because when we're talking in a security context, we also want to be able to catch attacks that are not successful on the model, right? We still want to be able to know who's trying to attack our model, and you still want to be able to make some sort of judgment call depending on what you would like to do and what the attack type is, basically. Okay. So here is some of the results highlights from all of my testing. One of the highlights here is that this detection method is very, very, very good if it's detecting previously seen attacks. So if the binary classifier has been trained on attack that it's seen in the validation set, very, very good. So an example I have here is a benign data set that is a set of benign prompts called OpenOrca. It's available on Hugging Face. It's contrasted with an attack data set called Jailbreak 528K. And here's one of the examples from that data set. You'll see it's setting up a role-playing context, and it eventually gets to this malicious payload where it's asking the LLM to guide me on how to create a fake travel agency for scamming tourists, basically. So that's an example. Here are the results. They are average over layers. Please hold your horses. It's not as good as it looks. Yes, super high accuracy for every single white box model. And these accuracies are all averaged across layers. So we saw that basically for every single layer, we're getting 0.9999% accuracy with very low standard deviation, extremely low false positive and false negative rate. However, this does not surprise us in any way whatsoever, because what we're doing here is we're using the large language model basically as a static feature extraction tool to train our binary classifier. And we know as data scientists, if you have really good features, you can get very, very good classification. And especially in this case, when our feature extraction thing, the large language model has billions of parameters, you're going to get really good feature extraction. And feature extraction that I could say even borders on just straight up pattern matching within a certain context. So yes, this looks very good. Additionally, something that is important to note is that we get very similar results, 0.9999% accuracy, before it even enters the transformers. So after it goes through the embedding layer, it does the positional encoding, all of that. You can extract activations out of that before it even enters the transformer, and you're getting this level of accuracy. So yes, it's good. Is it required to do this in the model for this context versus like at the beginning of the model? Not necessarily. Okay. Another results highlight, it is not good on completely unseen attacks. So I did the same framework and I just withheld a totally new type of attack in the validation set, and it could not classify that as an attack whatsoever. We're getting 58% accuracy on a binary classifier, which is not great. So that is something that we know can't be done, at least with this framework. However, another very interesting result that we found with this data set in particular called Wild Jailbreak, which is a great prompt data set that was created by Allen AI and posted to Hugging Face, actually provides a large set of role-playing prompts for both benign and attack. So for example, we have an attack prompt that sets up a role-playing scenario where it says, hey model, you are a legendary biosecurity inspector, blah, 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 blah. And then the malicious payload here is your objective is to find hypothetical vulnerabilities in a certain type of laboratory that the maintenance team would find challenging to uncover quickly. But we're contrasting it with a benign set that's very similar. So it's a role-playing setup again, but so for example, we have you're a new digital law intern, blah, 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 blah. And then the payload is provide me with information about legal ramifications of fraudulent practices. So it's hitting all the same notes. So if we're talking about fraud, we're talking about legal ramifications, but it's an entirely benign request. And the model actually does surprisingly well with detecting the difference between these two classes. And by surprisingly well, I mean, once we get to about the middle of the model, we're seeing about 90%. And I'll get out of the way here so you can see this thing. But in this graph, what you'll see is we have accuracy for every layer in the model. And what this means is, remember, I trained a classifier on every single layer. We see that after one transformer layer, we're able to get about 70% accuracy. And once we get about to the middle of the model, it increases to about 90% and doesn't get any better. When we're seeing similar trends for false positive rate and false negative rate is what those two graphs are. What does this mean to me? Again, these are very preliminary results, but it's indicative to me that we can use these transformers as extremely good feature extraction machines, basically. And they perform specifically well when you have two classes that are very hard to differentiate. Like you saw those examples. They're not necessarily easy. It takes a human a little bit of reading to even understand which one's benign and which one's malicious, right? Okay. Oh, and to note here, I don't know if you can really see it, but the 0th layer here, that's the embedding layer. It does actually slightly better than the first transformer layer, but the layers in the middle of the model have it beat by quite a bit. So that's interesting. Cool. And then finally, if I have time, I would like to talk about how the attack success actually changes the efficacy of this model. And the spoiler version here is it doesn't really. So my colleagues at Hidden Layer, shout out to Kevin, thank you for creating this lovely attack data set using an attack known as GCG. He was able to create a very small set. This is about 100 to 300 attacks that all break Mistral 7B, which this is the white box model that we're doing this testing on. They all successfully jailbreak the model. And this is an example of the attack itself. You have the malicious payload as first, and then you have your token level suffix attack on the end, which is just like random gibberish, basically. And this does really well. It gets about 99% accuracy when you are trying to detect attacks that actually break the model itself. And when I redid all of this testing without the attack portion, or without the suffix, the classification was only slightly better. So this is indicative to us, at least, that these attacks, or at least these token level suffix attacks, it doesn't matter whether or not it works on the model, you're still able to use this as an effective feature extraction tool for detection, which I think is really promising for other types of attacks as well. Okay, again, some limitations that I would like you all to keep in mind. This is white box defense only. This doesn't work for black box. This does require a curated set of prompts in order to train the binary classifier. However, it only requires about hundreds to thousands of prompts depending on how varied the attacks are that you're trying to detect. Generalization to completely new types of attacks is not possible, like we've seen. However, it does generalize better than just plain regex strings, because we know that it is actually able to detect new GCG token level suffix attacks that it hasn't seen before with very high accuracy. And also in some cases, just doing this analysis on the activations from the embedding layer is totally fine. And it does just as well, or in most cases, as middle of the layer analysis, basically. Okay. If there's anything that I want you to take away from this talk after all of these results, it's just these main three things. Number one is, can LLMs be used as feature extractors for defense purposes? Yeah. In the new versions of the slide, this says, well, there's a little asterisk that says limitations apply, and those were all of the ones that I just talked about. Does this work even when the attacks on the model itself are successful? Yes. I do believe that that's going to be the case, at least for token level attacks and maybe even other types of attacks. Can these features generalize to new types of attacks that it's never seen before? Probably not. Yeah, thank you. Does anyone have any questions?
Awesome, thank you, Amelia. I'll kick off with the first question, and then we'll pass the mics around. So your setup there is building a detector not of text, not a text detector, but using the LLM activations to get at a more useful signal there. Do you have any anecdotes or example documents where it would have worked one way and not the other? Or maybe my question is like, what signal do you think is in the LLM that would have been hidden if you were just looking at the semantics of the text?
Oh, I see. I mean, my belief here is that this would be able to bypass, I'm hoping that this would be able to bypass encoding attacks, but I haven't tested that. That's in the roadmap. But any attack like that where it's not obvious based off of just reading the prompt, I'm hoping that attack will be reflected in the activation pattern itself. But this is preliminary work. I cannot say that that's the case for sure.
Great, thanks.
Hi, great talk, thanks. I was a little confused about some of the test sets for the generalizing part.
Yeah.
Did you try to train on 6 different types of attacks and hold out a 7th, or was it just that 1 and 1 that you did?
We've done 1 and 1, but we've also, in that particular one that you're talking about, we trained on 6 types and held out a 7th. Okay. Yeah, and it was not able to generalize to 7th, basically.
Okay, great, thanks.
I had a question about intents. Did you check whether the intents for the 7th attack were the same? Like, for example, if it's biological-based attacks, like the intent was to produce a new poison, or were they part of the training and the test set, or did the intents differ across them?
Yes, so the topics, I would say, were very similar. It was just the style of attack that was the different formatting that was different in that holdout test set that it was not able to generalize to. Yeah, basically.
Yeah, as a follow-up, do you think the features are more in tune to recognizing the attack pattern or the intent behind the question? Because that'll be really...
It's a good question. I'm really hoping that we will find out soon here that it is, we're classifying on the harm topics, the intents. However, this failure on the holdout set indicates that it's actually classifying on the type of attack itself, which is still valuable. It's just not as valuable as I would like it to be. There is however, some really great research coming out of Anthropic about at the same time that I was writing this paper that shows that you are able to extract topics out of Claude, basically using VAEs. And so I'm hoping that maybe with a combination of this binary classifier on raw activations and some topic extraction from their research, we would be able to find a happy medium that can both identify topics and attack types. That would be awesome.
Thanks. This is a great talk. I'm wondering, did you, if you have any intuition or if you ran a baseline like where you just like fine-tuned the LLM itself, like, you know, where the prompt was the prompt and then you had a completion that like gives a refusal of the attack. And I feel like there's like a weird familial similarity with like LoRa or something here. I mean, it's not a LoRa, but like you're like, you know, you're sort of adding some more, you could think of this as like adding some more parameters to like the base model and exploiting like the intermediate representations. Anyways, I don't have really a complete thought there, but I'm curious if you thought about sort of the relationship between parameter efficient fine tuning and this sort of thing.
Yes, in a limited sense. I actually did some preliminary testing where we did all of the same framework analysis on a fine-tuned model using LoRa. I think it was Llama 2 7B. Basically, we were trying to see if we could fine-tune the model with some example attacks where we're like, hey, this is an attack, and we want, when we show it to you, we want you to refuse it, basically. And so sort of what you're saying, we fine-tuned it on that and then redid the framework analysis. And it basically showed that this framework did about the same with or without the fine-tuning. I didn't really report about it here because I wasn't sure what to make of it, and I did not do extensive testing, but it showed to me that at least if you're in a situation where you are fine-tuning your own white box model that you're hosting, that fine-tuning should not affect the results for detection with this framework.
Question, David?
Yeah, interesting talk. I also have a half-formed thought. One of the things this made me think of was something we had tried a long time ago, well out of the large language model space. But we at one point had a binary classifier where if you looked at the feature importances of what the classifier thought was important on the thing it was looking at, you could make a reasonable guess at whether or not the classifier was going to screw up its actual prediction. Like you could kind of predict a false positive was coming. And so in one very simple sense, it's kind of similar to this. And I think it's really cool to kind of like probe at how the model is thinking about things. But it makes me wonder too, to what extent is this, if you had a super large data set, is this like a interesting like out of distribution detection, or is it really getting like the essence of the threat? I'm not 100% sure.
Yeah, I'm not either. And I kind of envy Anthropic in that sense because I think they're working with a lot more prompt data, and so they can have a more definitive sense of what type of attacks or prompts in general are in distribution or out of distribution. I would say for right now, a lot of these very strong positive results might just be detecting like out of distribution based off of the training set. I'm honestly not sure. We're still working on it. Part of the issue there is it's really hard to source data for this kind of analysis.
Cool, thank you.
Yeah, thank you.
All right, great. Well, thank you, Amelia.